Very good. Welcome back. Uh, in the last couple of lectures or so, we have seen how it is that imposing a symplectic structure that is conserved by flows, by dynamics, leads to Hamilton's equations and Poisson brackets and all of that. Very good. So we have here one structure of the cotangent bundle that we have taken advantage of, and that leads us to very interesting flows on these funny spaces. What we want to do now is we want to ask the question, are there other structures, other symmetries in this problem that may allow us to single out those particular flows, those particular Hamiltonians that lead to interesting forms of dynamics? And the answer is that, well, yes, there is. We're talking about statistical manifolds, and if you have a statistical manifold, then immediately you have a metric. So the question that we could try to ask is, okay, if we have a metric structure, what additional symmetric or some interesting flows could we construct? Okay, so there is a problem in that the metric structure applies only to the simplex, not to the whole cotangent bundle. So we're stuck. The metric structure does not extend to the cotangent spaces. What we're going to do now is try to solve that problem, and we're going to extend that metric structure from just the simplex to the whole cotangent bundle, and then we take it from there. So how does that work? Let me go here and there. And so what we want to say is that if we have, so we want flows, we want congruences, potential forms of dynamical evolution on this cotangent bundle where S is the simplex. Then we'll worry about embedding this in larger spaces and all of that. So we found that if we have a symplectic form, then flows that preserve the symplectic forms lead to Hamiltonian flows. Curves that satisfy Hamilton's equations, the whole structure of Poisson brackets, and all of that. So what we're going to propose next is that if we have a metric on the cotangent bundle, then we would like to impose, so a metric G, we would like to impose that the flows we want are such that not only they preserve the symplectic form, but they preserve this other symmetric tensor, antisymmetric tensor, symmetric tensor. We want to preserve both. Then this will lead to what's called killing flows. After the person in the 19th century who actually studied what kind of curves you can have on metric manifolds that preserve the metric. So eventually what we would like to have is both Hamiltonian and killing flows. So how do we do this? The problem. Okay, first, problem. The simplex has a metric. The cotangent bundle does Not. So we want to invent a metric for the cotangent bundle. And the way is that arbitrary? Of course it is. There is no way to assign a metric to a manifold that's not going to involve some sort of arbitrary choices, unless the manifold happens to be a statistical manifold like S is. So statistical manifolds are special. So the issue is then that in the process of assigning a metric to the cotangent bundle, we're going to make several assumptions. We're going to introduce symmetries. We're trying to say that this is very elegant and inevitable, but of course it's not. Nothing we do when we're trying to use inference is inevitable. Remember, the laws of inference can help you do quantum mechanics, but they also help you do the stock market. They also help you do medical trials. They also help you do economics. They're tools for reasoning. And the tools for reasoning are not, well, they're supposed to be generic enough to handle many different problems. Here, we are not interested in many different problems. We're interested in just one, the one we want to call quantum mechanics. So, of course, we have to make assumptions. The assumptions may seem natural once you develop your intuition enough to recognize, oh yeah, of course, that's quantum mechanics. But at the moment in which you're just doing mathematics, which is what we're doing here, then the assumptions may be at best elegant, not inevitable. Very good. So let us do it. How do we do this? So what we're going to do first is we're going to come up with a metric for the embedding cotangent bundle. So this is the guy that has 2n dimensions. And the way we're going to do this is the following. You may recall that if we have a simplex, the simplex S, which is a simplex in n minus 1 dimensions, has the geometry of a sphere. In fact, we can embed it as n minus 1 into a larger space that is spherically symmetric. The metric for that was, this is the metric that you can just write down for a generic spherically symmetric space. But the actual way we derive the metric that I'm going to be writing down, the line element that's implied by this metric, was by the argument of doing Markovian embeddings. The invariance under Markovian embeddings is that led us to a metric, and this metric happens to be a spherically symmetric metric. The actual formula is something nasty like this. These are functions of the sum of the normalization of the probabilities. And then you have here a factor that involves theta I equals 1 to n. So this is, here we're just dealing with the simplex Sn-1 embedded into the n-dimensional S plus 1. So the thetas go from 1 to n. And these guys here go squared. And then we have another term, 1/2 theta, another function, b theta, and then we sum 1 to n of 1 over theta I delta theta I squared. Very good. So that is the spherically symmetric metric of Sn plus 1. So what we would like to do is, this is as, oops, let me see. There we go. This is our, we proceed to find the metric of the cotangent bundle T star S plus 1. We're going to perform in three steps. One of them is the recognition that the simplex has the geometry of a sphere, and therefore it can be embedded into a spherically symmetric space. This is step A. In principle, we have already done that. We're going to repeat all of this again now, so you need not worry, although the equations get messy very quickly. The second step is to extend the spherically symmetric metric of S plus 1 to a spherically symmetric metric for T S plus 1. So this is the step that we're going to work on, and we need to be very careful about all the assumptions that we're going to be making here. I've said this once, and I'm going to say it again, and then I'm going to repeat it again so that it sinks in. We have to make assumptions. There is no way to take the metric of one space and enlarge it to be the metric, extend it to be the metric of a larger space without making some assumptions. And the assumptions we want to make are those that are going to be relevant for quantum mechanics. So we want to extend the spherically symmetric metric, this metric that we see here, from the space, from the base space S plus 1 to the full cotangent bundle. Then finally, and this is going to be the very easy step, and we're not going to do it today, finally is, given the metric of the embedding, the extended cotangent bundle, we can find the induced metric on that we really want. This is the metric that we want, the cotangent bundle, the E phase space. So this is the phase space, the epistemic phase space. This is the space where we want our dynamics to happen. So today we focus on that step, how to extend the spherically symmetric metric that we have here to twice the number of dimensions, from n dimensions to 2n dimensions. Before we proceed further, have you noticed how I've been saying sphere, spherically symmetric, spherically symmetric, spherically symmetric? Everything is the spherical symmetry appears to be the crucial element when we do this extension from n dimensions to 2n dimensions. So why is it that I insist on the spherically symmetric, on the spherical symmetry? The reason is that this is what we need for quantum mechanics. So what I'm going to write down now, I'm going to write down an equation that is not going to be obvious at this stage, but once we reach the end in a couple of lectures, we reach the end of this argument, you're going to be able to see with the benefit of uh, of after sight, with the benefit of something, you're going to be able to look backwards and say, ah, yes, that is when we made the whole theory quantum mechanical. So what is it that I want to point out? Uh, so an aside, just a fact, interesting mathematical fact. If you have a symplectic form and you want flows that preserve the symplectic form, any transformation that preserves symplectic forms are going to be symplectic transformations. They're canonical transformations. Okay, so if you have a group of symplectic transformations in two n dimensions, it's a phase space, right? The coordinates and the momenta, two n dimensions. And you're dealing with real numbers, which is what we have been doing so far. And then you look at the group of orthogonal transformations in two n dimensions over the reals. So these are rotations. This is where the spherical symmetry comes in. So we have those transformations that preserve the symplectic form. Then you have all of these other transformations, just rotations. They preserve distances. So these are the ones that are going to be, if you have any sort of segment of a given distance and you do rotations on it, you're going to preserve its size. The metric preserves the metric, right? So now, what happens if you consider transformations that are both canonical, symplectic transformations, and rotations? So you consider the intersection of those two groups. The wonderful mathematical fact is this is the unitary group in n dimensions over the complex numbers. So this is just a mathematical fact, devoid of any physics in it. But if we already have the symplectic transformations, the canonical transformations, and somehow we force the issue and we impose rotational invariances in two dimensions, in two n dimensions, somehow out of all that, complex numbers are going to emerge, and we're going to get the unitary transformations that we need for quantum mechanics. So, with malice of forethought, that's exactly the kind of thing that we're going to be doing. If anything makes you think in all of this that we could derive quantum mechanics without knowing what the founders of quantum mechanics actually derived, forget it. It doesn't happen like that. You really have to know the results that you want to achieve in order to get to them. The goal of all of this endeavor is not so much to discover quantum mechanics, but to discover the assumptions that you need to make in order to get to quantum mechanics. We're in the business of discovering the necessary assumptions, not the final theory. Of course, in the process of discovering the assumptions, you do end up learning a lot about the final theory, including ways in which you can probably or possibly generalize it. But that's another issue. If we didn't know that at some point you wanted quantum mechanics, nowhere along the way would one have thought of having symplectic, well, maybe symplectic groups, yes, but the rotations, I doubt it. Very good. So let's do it. So the first thing I want to do is a short comments on spherically symmetric spaces. let's discuss a little bit spherically symmetric spaces so that we understand their geometry a little bit better. Let us start with the possibly simplest phase space that we could imagine. The simplest case involves the one simplex. This is what describes a coin in which you have the probability of heads, the probability of tails, and of course the two add up to 1. And so this simplest simplex, if you plot theta 1 and theta 2, the simplest simplex is going to be just that line. So this would be S1, which here you see embedded in the two-dimensional S plus 1 has d equals 2, t s plus 1, the space we want a metric for, has d equals 4. So this is the dimension here is n equals 2. The dimension here is 2n equals 4. So this is a little bit disappointing. The simplest possible phase space you can imagine is 4-dimensional, which makes it difficult to visualize. So what is the metric of a 4-dimensional spherically symmetric space? All right. Well, what is a spherically symmetric space? If you have a funny sort of arbitrary space, the space is going to be spherically symmetric if every point in the space can be put on a sphere of dimension n minus 1, right? So this a spherically symmetric space is a space that looks like an onion. The space has n dimensions. You can foliate it. You can find every point on some kind of layer of the onion that has n minus 1 dimensions. So let us write that down here. The simplest possible phase space then can be foliated t s plus 1 can be foliated into 3 spheres, 3-dimensional spheres. And the metric of such a space, the line element, we're going to write it as follows. And better. Introduce the generalization of spherical coordinates. So what this means is that there is going to be a radial coordinate, and we're going to see in a second what that might be. And then there are 3 angles, alpha 1, alpha 2, and alpha 3. If you were doing 2 spheres, if you were two spheres, a 2-sphere, you might want to use spherical coordinates are theta and phi, right? You measure theta from the z-axis and then you measure phi azimuthally about the z-axis. Very good. Here, because we're dealing with 3 spheres, we have 1 radius and 3 angles. And what's the metric? The metric, so this is an aside, the metric here is going to be given by the line element. and it's going to be delta r squared plus and r squared the omega squared. Well, in a second, I'm going to tell you what the omega is. In fact, I'll do it first, and then I'll come back. Where the angles, this delta omega squared is going to be delta alpha 1 squared plus sine squared alpha 1 d alpha 2 squared. You see, if you are if you were dealing with two spheres, this would be d theta squared plus sine squared theta d phi squared. Because we are dealing with 3 dimensions, you have to add an extra piece here, sine squared alpha 2, and then multiply by the alpha 3 squared. So you can recognize that this second piece is as if you have a 2-sphere. This first piece here is another 2-sphere. So this is how you build it up. Very good. You can see that this is a standard, straightforward generalization of what happens for 2 spheres. Now let's go back here. If this is all the metric you have, then you can appreciate that if you set the angles to 0, you're looking at a little segment that happens at constant angles, then this is the radial distance, right? The interpretation of R is that it is the distance between 2 spheres that differ by delta R. Similarly, if you are on the surface of one of these spheres, you set R equals constant, so dr equals to 0, and this gives you the distance measured on the surface of one of those spheres. Very good. This is flat space. This is a flat space. What we mean by a generic spherically symmetric space is that every point is on the surface of some sphere. So we're going to have a distance like that, but the scale, the radius r that measures distances on that surface of the sphere can be something else. So we're going to rescale those tangential distances on the surface of a sphere by an arbitrary positive function. And similarly, when you have 2 layers of the onion that are differing coordinates by delta r, we're going to say that if you have a delta r here or another, the actual radial distances need not be given by the change in this radial coordinate. They can be anything you want. So we're going to impose here another arbitrary positive function. So this is what a spherically symmetric space looks like. If you set delta r going to 0, then what you have here is the metric for a sphere of radius. So interpretation. If we set delta r equal to 0, which is the same as saying r equals constant, what we get is spheres. The metric for those spheres is going to be b r squared d omega squared, so that the distances on the surface of the sphere are going to be given by b to the 1/2 r d omega. and this plays the role of the radius. It gives the scale for distances on the surface of a sphere. On the other hand, if we set the angles all equal to 0, we set the angles all equal to 0. What that means is that you're looking at the actual distance between, say, the North Pole and the North Pole and the North Pole, right? You're aligned on North Poles. And so what this means is that we truly have a radial, so the metric, let's write the metric for those. Then, so this is just distances between the North Poles. And what we have there is that delta L squared. Let's look it up back here. It's this piece here is going to be A d r squared. And so the radial distance is not dr, but the radial distance is dl given by 1/2 delta r. This tells you that the radial coordinate r is not a radial, it's not the radius, the distance to the center. There may not be a center for all we know. R is just a coordinate that labels spheres. R is not a radial distance. The interpretation of R just labels these concentric spheres. Very good. It's convenient for reasons that we'll see in a little while. Instead of talking about the radius r, which is positive, let's talk these as functions of r squared. It's a good convention. It doesn't make any difference. Very good. So now we have our generic metric. Here it is. Very good. If this is, yes. Now you probably see that what we're doing here is we're dealing with the simplest possible case in which the base space S plus 1 has 2 dimensions and the phase space has 4 dimensions. And this already led us to metrics that have angles coming up in forms like this. For two n dimensions, not 4, what we're going to get is something like a metric of exactly the same form we had before. Plus the function of r squared, the omega squared, where this, I'm using deltas there, this little guy here is something pretty awful, but it's more or less along the same structure. In fact, here we have a radial coordinate, and then we have 2n minus 1. We have 2n minus 1 angles. So what we're going to have here is something like delta plus sine squared alpha 1, and then here we have a parenthesis, and then this is the alpha 2 squared plus sine squared alpha 2, and then we have another parenthesis, and then this keeps going. Here we will have d alpha 3 squared, and then it keeps going. And then finally, you conclude with something like the very last one is going to be the alpha. So this, you have all these nested brackets here, the alpha 2n minus 2 squared plus sine squared alpha 2n minus 2 multiplied by the last angle 2n minus 1, and that concludes it. And then you have a bunch of more brackets and then the last two, and so I hope you appreciate it's pretty messy. It's pretty messy, but we have it. Okay, so now let us try to remind ourselves of what it is we're trying to do. What we have here is a space in general that involves thetas and pi's. So we have a space that in which each point is determined by thetas and pi's, the coordinates on the base manifold and the coordinates on the cotangent manifold. So the issue for us is you look at this metric. This is a generic spherically symmetric space. Generic spherically symmetric space. The metric is a mess. And you see, okay, very good. I have R's and I have alpha 1s, alpha 2s, blah, 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 all the angles. So the question is, where is theta here? Where is pi? Fine, it's spherically symmetric, but how do we actually match this generic spherically symmetric space with those variables that are the dynamical variables of interest? This is where assumptions will come in. So, in order to make it a little bit more natural or a little bit more explicit, how it is that we associate a theta to these coordinates, where is the theta hiding in all of these variables, and where is the pi hiding in all of those variables. What I'm going to do is change from spherical coordinates from these spherical coordinates to pseudo Cartesian coordinates. Now, why pseudo Cartesian coordinates? Remember, this is spherically symmetric. It's a curved space. So, of course, you cannot find Cartesian coordinates. At best, if you have a curved space, you can find Cartesian coordinates in a sufficiently narrow region, right? But you cannot extend that everywhere. So Cartesian coordinates, you can't. The reason I'm going to call these pseudo-Cartesian coordinates is that given these angles and given this r squared, you can always define a coordinate x1, which I'm going to call it r cosine alpha 1. You can always do that. Nothing prevents you from saying, look, I have an angle here. I'm just going to do that. If you think in 3 dimensions, this would be like r cosine theta. It's the projection on the z-axis, right? So if this were flat and you were in 3 dimensions, you take a generic vector, project on the z-axis, right? And then once you have projected on the z-axis, then you will go ahead and project on the xy plane. You will project in the other. And when you project in the other side, you would have something like r sine theta, right? You project it down. Now you're going to pick another axis and project cosine phi, cosine alpha 2. And then you project on the other one, it's going to be sine phi, right? But then here we're not done. We not have 3 axes only. We have as many as you want. So once you project it with the second sine, you still have to project cosine and sine again. So you keep going. Sine alpha 1, sine alpha 2, because I projected cosine 2, alpha 2. Now project on the sine. But now you have to project again cosine alpha 3, and you keep going until the whole thing ends, and then you end when let me see, let me put 2n minus 1 is going to be r sine alpha 1 sine alpha 2. Keep producing sines, and you get to sine and eventually you end up here with a cosine alpha 2n minus 1. And then for the very last one, you get r sine alpha 1 sine alpha 2, and then you end up with sine 2 alpha 2n minus 1, and you're done. These are the pseudo-Cartesian coordinates. They're pseudo because they're not Cartesian. They have the same mathematical form as Cartesian coordinates in a flat space, but they're not Cartesian because r is not a radial distance. It's just a positive quantity. Okay, very good. So we have it. In terms of these coordinates, life simplifies. Well, it's still ugly, but life simplifies because we can sort of understand the math much better. So, for example, if you the interpretation of these coordinates is a mess. But you can still take their squares. So even though we do not know what the interpretation of these x1, x2, x3 are, just they're given by these formulas, it is nevertheless the case that the sum of these coordinates, let's call them by the letter A, the sum of these coordinates squared, A goes from 1 to 2n, is equal to r squared. You can sort of see that because if I were to take the last two, square them and add, the cosine squared and the sine squared disappears, and we're left with the cosine from the first and the sine from the sine and the sine, and which then we can actually, when that's the sum of the squares, when you add with the next one the sine squared from this guy and the cosine from the previous line, they also disappear, and so you can build it up back. Try to do it. Try it in 4 dimensions and see what you get. So that is still true, and what we want to do is we want to take this metric and we want to rewrite it in terms of these pseudo-Cartesian coordinates where you have a bunch of angles and everything. So we want to figure out what dr is in terms of these x's. And so we can do that because we see immediately that if we take differentials here, we're going to have the sum of 2 xa dxa, a equals 1 to 2n. There is a 2 which cancels when I do the same thing on the other side, 2r dr. And so if we want to know what dr is, all we have to do is just divide here by r, and we have what dr is. This is the object that we're going to insert here. Now we have to do exactly the same sort of thing and rewrite these angles in terms of these x's. And it's a little bit more complicated to do that, but it is nevertheless true that if you were to do the dxa's squared and add from 1 to 2n, this object here would give you the r squared plus r squared d omega. So how do you know that that would happen? Well, if this were a flat space, we can figure out the mathematics of these transformations, and that is what you would get. The fact that it is not a flat space does not change the fact that the mathematics remains the same, because the formulas that connect the x's and the angles are exactly the same. So we have here an expression for r squared d omega squared in terms of this guy, and the dr is something that we have from there. So what this means is that the metric that we obtain in these pseudo-Cartesian coordinates is going to be let's go back here. We're going to have the a dr squared. We have a dr squared, and so I'm going to write the dr squared here. And then we have plus b r squared plus b r squared d omega squared, right? So plus b r squared the omega squared. The r squared, the omega squared is going to be given by that expression. That expression minus dr squared. So the minus dr squared, I'm going to write it here like so. And I think we're done. Maybe I have a mistake or two somewhere, but basically, yes, this is. Let me see. I made a mistake. Of course, I made a mistake. The r squared, the omega squared is this piece, and then here we have the a dr squared. There is a mistake here somewhere. So some part of the algebra. Gotta fix that. Minus b r squared. Let's leave it there. I'll fix it later. So this is basically the equation that we wanna have for spherically symmetric spaces. Very good. So question: where is theta? Where is pi here? So now that we have an equation of this form, still bothers me that okay, r squared d omega squared is this piece here. I had a wrong definition previously for the A's and B's. When I rewrite this, I'll give you the right expressions for these expressions here, for these quantities here. Very good. Let us continue. So where here is theta and pi? Very well. Here is assumption 1. For the simplex itself was spherically symmetric. Sn minus 1 is a spherically symmetric space. Theta equals constant. Theta equals 1 is is a piece of a sphere. So what we're going to say is that for S plus 1 is also a spherically symmetric space. And for this space, we're going to say that this equals constant is a sphere. So where are the spheres here? The spheres in this space are the spheres are selected by setting R equal to a constant. Okay, here the assumption is this one. This thus theta equals constant corresponds to R equals constant, where R squared is equal to the sum of these coordinates squared. So we have made the first correspondence between the generic pseudo-Cartesian coordinates and the dynamical variables. We are going to say that R squared is going to be theta. Here is the assumption. Theta is the same as R squared. Second assumption. Assumption 2. Very good. The reason we are interested in these spherically symmetric spaces is that so here we're saying for t star s plus 1, we're going to, this is the assumption, right? Now, the reason we're interested in all of this is that t star s plus 1 is a phase space. What that means is that to every coordinate there is a conjugate momentum, right? To every theta there is a pi. And if the coordinates are these x's, we're going to say that to every x there is another x that is the momentum. You have the phase space. If this is a coordinate x, that's p sub x, the momentum conjugate to it. So we're going to say, but this is an assumption, is that all the x's, the pseudo-Cartesian coordinates, can be paired. They can be analyzed in pairs. This is where the symplectic structure is coming in. To every x, there is another x that is the momentum conjugate. And so if you have x1 and x2 and x3 and x4, and then you have x2n minus 2 and x2n, we're going to say that these can be paired. Of course, whether I put 2 or 3 or 3 and 2 doesn't make much of a difference. This is completely symmetric. So we're going to call this Xi and eta 1. This is going to be Xi and eta 2. The new label counts which pair, and this is going to be Xi and eta n. So the idea is that the odd ones, x 2i minus 1, x 2, and the even ones will be relabeled as Xi I eta I. So here I just changed the name of this thing. So instead of having to count from 1 to 2n, I'm just going to count pairs 1 to n. And the new metric, we can read it from here. It's going to be exactly this metric here. It's going to be something like delta L squared is going to be AR squared minus BR squared. And here I'm going to have the sum over pairs 1 to n. And the term that I have in mind here is x delta x. So this is going to be Xi delta C plus eta delta eta. All of this goes squared plus BR squared R squared, and then the sum of the delta x's squared. So here the sum from I equals 1 to n of delta Xi squared plus delta eta I squared. Very good. So that's the metric. Okay, very good. Where R squared now is I equals 1 to n, and we are summing these guys squared and eta squared. Very good. You see that I haven't done anything here, right? But I did do something important. I actually said, look, to every theta there is a pi, and so we're going to say which are the coordinates, the x's, and which are the conjugate momenta, the etas. And now on looking at this expression, I'm going to make my assumption 3. The assumption 3 says, oh, but wait a minute, wasn't it true that this is the sum of the thetas, which is the sum of the theta i's as I goes from 1 to n? Well, on comparing this equation for the sphere with this equation for the sphere, I'm going to make the assumption that these two guys match the thetas. So this is the assumption. It's not just that the sums match, but that each term here matches. So basically what one is doing once you start trying to visualize what's going on with these two n-dimensional spaces is that if you have 4 axes, you can single out a plane of just 2 axes. That's what I've done. And then another plane of 2 axes. And I'm going to say that the theta 1 corresponds to one plane, the theta 2 corresponds to the other plane, and so on. Each plane corresponds to one value of the thetas. this, remember the goal is we have this spherically symmetric space with generic coordinates that we do not know what possible physical meaning they might have, and we have to somehow put thetas and pi's there. So how do we do it? Well, this is how I'm doing it. Identify what you want the spheres to be. That's part of it. Then select what you want the canonically conjugate coordinates to be. That's this other second assumption part. Finally, you say, okay, how are the probabilities that were just total normalization being R squared distributed among the various planes? So we're distributing the probabilities according to something that has to do with the symplectic structure. Planes, the twos, right? One coordinate and the canonically conjugate one. Very good. But once you're here, you say, oh my God, this is exactly the kind of thing that you should say the good coordinates in this spherically symmetric space are not quite these pseudo-Cartesian coordinates xi and eta, but we should choose pseudo-polar coordinates. And for pseudo-polar coordinates, I'm going to use the radius and a polar angle. So if here you have in one of those two-dimensional planes, you have these coordinates and that coordinate, and they satisfy psi squared plus eta squared equals theta I, I'm going to think of this guy as a radius squared. Theta I square root, and I'm going to use this guy here as an angle phi I. So see, I'm going to write it as theta I square root cosine phi I, and eta is I 1/2 sine phi I. Assumption 4. The last assumption. So right now, when we look at the metric written in terms of these x's and etas that are supposed to be canonically conjugate, we see that these guys here are you see where the thetas are going to come in. The magnitude of c squared plus eta squared, that's where the thetas are coming in. But where are the pi's? Well, okay, that's the last step. When we say, look, the reason we separated these two is that we intended this to be canonically conjugate to that one. So if this c is a coordinate, that's its momentum. Well, this transformation, the transformation above, this transformation is canonical. You can check that. It's not difficult. I'm not going to do it because I don't want to stretch the class too long, but it's actually pretty simple. So that means that if xi and eta are canonically, conjugate, then theta I and phi are canonically conjugate. So here we go, assumption 4. We identify the phi's with the pi's. conclusion, we're done. We know exactly where all the thetas and pi's are going. They're going into these expressions for the coordinates. So, conclusion, when we substitute these expressions back into this metric, it's actually pretty easy to do that. The metric of t star s plus 1 is given by the line element, and let's write it out. This is going to be a function of theta, and here we have delta theta I squared, no, I equals 1 to n squared plus another function b theta, b of the function of the normalization, and here we have I equals 1 to n. The first piece of the metric is delta theta I squared divided by 2 theta I plus 2 theta I delta pi I squared. And we're done, where A is equal to those little a that we had before minus b divided by theta, and b, there is a 4 here, and b is 1/2 b, and then multiplied by theta multiplied by b, which is a function of the normalization again. So here we have the metric. We're done. Notice that if you just look at the distances between 2 points in the cotangent bundle that have the same pi, so delta pi equal to 0, you reproduce exactly the same metric we had before for the spherically symmetric, for the s plus 1, right? The embedding space for embedding the simplex. So this metric includes, as a special case, the information geometry of the simplex. It's there. It's hiding there. Of course, we built it this way. We imposed all the symmetries required to do that. Other comments that we might want to do. I'm going to make the same emphasis, draw the same emphasis on the fact that we have made assumptions in order to embed s plus 1 into the cotangent bundle. Of course, you need to do some assumptions. The assumptions that we have made are such that when we pay attention to the spherical symmetry that's going to be required to do quantum mechanics, we have paid a lot of attention to the fact that the underlying simplex is spherically symmetric, and so is its embedding space. So we're looking for spheres. This is the first assumption that we impose. The radius of the sphere is given by the normalization. Second assumption is the fact that being a phase space, it makes sense to separate this into canonical pairs. That, of course, is still an assumption. And so what we do here is identify each one with a canonically complex conjugate momentum. And so At this point, we just have r squared in terms of coordinates and their momenta. And when we do the next assumption here, it's going to be to isolate each one of these planes with one of the probabilities here, and then we put pseudopolar coordinates because it totally makes sense that if you want to change this and change that while keeping the theta fixed, this is the right natural way to implement it, something like that. Since the transformation is canonical, then phi is canonically conjugate to the thetas, and that means that it makes sense to draw the last step. Very good. I think that this is enough for today. What we're going to do next time is we're going to use this metric that we have derived for the cotangent bundle. We're going to find the metric for the cotangent bundle of the simplex T star S. And there we're going to start to see yet another interesting feature of quantum mechanics emerging. See you then.